Welcome back to Basic Logic, an open introduction. I'm Dr. Nick McGinnis, and in this video, we're still working on Chapter 8 of For All X, the Lorain County remix, an open source logic textbook that you can download freely online. I encourage you to do so because I'm going to be relying heavily on the practice exercises inside this textbook, because logic is not something that you can just conceptually grasp. It's something that you have to work at. It's a skill that you're going to have to develop by doing exercises and problem sets. In the last video, I introduced the natural deduction proof system. This is a syntactic system whereby we manipulate strings of sentences according to predefined rules in order to generate new sentences. What happens here is we assume the premises of an argument are true, and we kind of construct what follows from there on the basis of rules. This works because there's only so many logical forms in sentential logic, roughly corresponding to the sentential connectives and their negations. Now, in the last video, I talked a little bit about some introduction and elimination rules. For example, the elimination rule for an AND is straightforward. Any AND statement allows me to break down into its connecting components. So if I have P and Q, I can grab the P independently of the P and Q sentence, no matter how complicated P actually is as a subsentence of the main logical operator AND. But some rules are going to be a little bit more complicated than that. The conditional introduction rule is a good case study of what I call the conditional proof, how to make an if. To create a conditional in a natural deduction system, we again mirror our natural thought process. I say something like, suppose that were true. If that were true, this other thing would follow. Now remember, in a conditional, the truth table is clever. The antecedent doesn't need to be in fact true. Only if it were true, the consequent would follow as well. So to build a conditional, I don't actually need a true antecedent. I just need to pretend as if an antecedent is true and find out what would happen if that were the case. So I could say our natural line of reasoning works like this all the time. So all we're doing is introducing a notation system to make that clear. I can think like, well, okay, yeah, suppose I robbed the bank. Then I would have to be in two places at the same time. Copper, you see? Why am I doing a bad gangster accent? It's 30s. Which is impossible, so I didn't rob the bank. For this argument to work, I have to introduce the P of the if P then Q as kind of a hypothetical. I'm not saying I robbed the bank. I'm saying, well, look, if I did rob the bank, I'd have to be in two places at the same time. So how do I represent this hypothetical in our deduction system? Well, here's how the notation system could keep it clear. What I'm going to do is I'm going to introduce, right, notation is everything. Honestly, how you write stuff down in logic is 90% of the game. So what I'm going to do is I'm going to just introduce a vertical line. And that vertical line is going to be separating my hypothetical what-if scenario from what I know to be actually the case that follows from my premises. So what is directly next to the numbers is what I assume to be definitely true. So suppose I have premises. If P then Q, if Q then R, those are my premises. I want to create a conditional. I want to create, well, therefore, if P then R. So this is just transitivity, right? This could be any example. If I'm out, I'm drinking. If I'm drinking, I'm having a good time. Therefore, if I'm out, I'm having a good time. It's a great example. Actually, I don't drink. Moving on. So how am I going to create this conditional? I don't know that P is in fact true. What I want to say is, like, if P were true, this would happen. So what I'm going to do is I'm going to add a little vertical line here that's going to be separate from the main line. The main line represents everything I know to be true. What do I know to be true right now? I know that if P then Q and if Q then R. These are my premises. I'm assuming their main logical operators are true. So I'm going to create a vertical line, and I'm going to say, okay, hypothetically, assume, let's say P is true. If P is true, then Q is R. How do I know that? Conditional elimination, which is a rule we already have. But if Q is true, then R is true. Now here comes the tricky bit. I've shown that if I assume P, one of the things I can construct in a sub-derivation, like a little sub-line of construction, is R. So what I've shown is if P, then R, on the assumption of P. So what have I actually shown? I've shown that if I assume P, then R would follow. So now I can stop that line, that vertical line separating my hypothetical from the rest of my derivation, and just discharge or place my new construction on the main line, because I know that new construction is true on the basis of the premise. And what I am bringing back to the main line isn't P or R, it's if P, then R. The idea is here, any assumption that I make can be the antecedent for a conditional I'm constructing. Any assumption I make, can be the antecedent for a conditional I'm making, and the consequent can be any of the subsequent constructions I've made on the assumption of P, or whatever I've assumed. So what I'm going to be bringing back to the main line is if P, then R. All right, so let's say P is true. If P is true, then Q is true. But if Q is true, so is R. So if P is true, R is true. That's what I've actually proven. So this is on the main line. It's not separated by this vertical, oh, this is just a hypothetical line, because I know this is true on the basis of that. If P, then R. Now, if you don't believe me, just do the truth table. If you do the truth table, you'll see that if P, then R is a valid conclusion that can be derived from the premises that we have. The important thing to remember is that the line here that we created, the vertical line, separates the hypothetical from what we already know. The hypothetical, what if, is going to be the antecedent of a conditional we're constructing. So if I'm introducing a conditional, what I want to introduce is the antecedent of the thing I'm interested in. Anything following from that hypothetical could be, that's up to you, could be the consequent of that conditional. So actually, what's my next slide? Okay, so let's do something else here. So suppose I have the same argument. If P, then Q. If Q, then R. And I want to show that this is my target sentence. If P, then R. Let's just do a truth table very quickly, right? So imagine this is false. My conclusion is false, but the premises are true. If this conclusion is false, then P must be true, but R false. Let's say P is true, but R is false. However, the premises have to be true. P is true, but R over here is false. But the premises have to be true. So this has to be true, and this has to be true. All these premises here have to be true. So true, true. Can Q be false? Q can't be false, because if there would be true, false, false, Q has to be true. If Q is true here, then Q must be true here. So true, true, true. So, right, we have a contradiction. Q has to be true. R has to be true and false simultaneously. So the short truth table version, right, very quickly, I don't know if I went too fast there, shows that it is indeed a valid entailment. How are we going to do it in the derivation system? If P, then Q. If Q, then R. What am I interested in? I'm interested in if P, then R. So what I need to do, line 3. Right, so now the cursor's blinking here. It's your move. What are you going to do? All right, my target sentence, the thing I want to build and prove that it follows, is a conditional. So I know I'm going to need to use conditional introduction. All right, how does conditional introduction work? I create a vertical line. I don't know how long it's going to be, but I'm probably going to have to make a few moves. This separates it from the main line over here, which is everything I know to be true. Right? I know this is true, I know this is true. Now I'm saying, what if P? What if P? Well, if P, then Q. So now I'm going, this is like a sub-assumption that I'm making. Why am I making it? Conditional introduction. Right? I'm just going to, this is like my little notation. But why did I do this? Oh yeah, because arrow I for conditional introduction. And now if P is true, then Q is true. How? Because 3-1 conditional elimination. Now you might go, well, wait. Why are you allowed to use P on this line when if P, then Q is on the back line? It's back on the main line. That's all right. You are allowed to make reference to everything prior on this side here. So I'm assuming P is true, and I already have these things. So I already know that these things are true. So then I can, okay, so I know this is true, and I'm saying, hypothetically, let's say P is true. If P is true, then Q is true. And if Q is true, now I have it, and I'm still on this line, then R must be true. Why? Because I have Q on line 4, and I have 2. It's another conditional introduction, but it's all happening, all the action is happening here. What I need to do is come back over here. How do I come back over here? I have to discharge something that I hope is true on this line. How do I do it? Well, this was a hypothetically, so if I assume this, that'll be true. So I just restate what I've proven. When I'm going back this way and I discharge my conditional introduction, I'm not doing anything special. I'm restating what I've just shown. What I've shown is if I assume P, I can derive R. That's what I've shown. So given that I've already shown that if I assume P, I can derive R, I can just rewrite what I just did. If P, then R. I'm not introducing something new. I am rewriting what I've already shown. Now, of course, the natural derivation system is open-ended. You can prove what you like as long as you follow the rules. So let's actually do something slightly different here. What if my target sentence was, if P, then either R or Z? Well, where did Z come from? How can I possibly construct that? Well, that's actually pretty easy. Now, you remember we have a rule called disjunction introduction. And this is kind of where the fun, creative nature of the natural derivation system really comes into play. Because if I wanted to prove that this argument was valid, I'd have 1, 2, 3, 4 atomic sentences, and that's a long truth table. That's 2 to the 4 rows. Now it's a very quick derivation. But how am I going to get Z? Remember, disjunction introduction is a rule, and I can definitely use it whenever I like. I can use it on this line. On this hypothetical line, I know R is true. And if I know R is true hypothetically, I know that I can use disjunction introduction on line 5 and introduce Z, because if R is true, then either R or Z must be true, assuming P. So this line means this is all happening assuming P. So if I assume P, one of the things I can construct is R then Z. So again, I can just go back to the main line and say, hey, I'm just going to rewrite what I've just discovered. What cool thing did I just discover? If P, then either R or Z. How do I know that? If you go back to lines 3 to 6 here, conditional introduction. That's what I just did. Go back and look. Look, I proved it. I said if I assume P, I get that. So I'm just rewriting what I've just shown. And that's how conditional introduction is going to work. There's going to be a number of conditional style proofs that we're going to be introducing in our derivation system here, and they're all going to work roughly the same way. You create a vertical line, separating out your assumption, and then before you finish, this is important, you have to go back to the main line somehow. How do I go back to the main line? Each rule will tell you when it's safe to do this. In conditional introduction, you could do it by grabbing any one of the things you constructed and creating if P, then that. So I could have gone if P, then Q. I mean, I already have it, but I could have. If P, then R. If P, then R or Z. Anything else I construct, I could go if P, then any of the things on the line, and I say that I discharge that as a conditional. Okay. So, let's look at this one. Here's another interesting conditional to build. So I say I have either R or F. Now I say I want to build if not R, then F would be true. Now this is a pretty intuitive argument, right? It's one or the other. If it wasn't one, then it would be the other. Sure, if it wasn't one, it would be the other. So how do I build that? Well, easy. I assume not R, right? And I create a little vertical line there. And I say, look, if not R, then by disjunction elimination, I can get F. Right? Disjunction elimination says, hey man, it's one or the other, but it's not the one, so it must be the other. So I can assume not R. I get F, right? Because either R or F, not R, therefore F. So hey man, when I assumed not R, I could derive F, which means if not R, then F. So in the course of these two examples, arguments, we've made use of premises, assumptions, consequences of assumptions, hypotheticals. Right? On line 3, there was a disjunctive syllogism using our assumption together with the premise on the main line. Right? Everything to the left of an assumption can be used. Why am I pointing this out? Because you might be thinking, how many assumptions in a proof can I have? And the answer is as many as you like. That's kind of the cool thing. I can nest an assumption inside another assumption. As long as I follow the rules as I move back to the left and I discharge conditionals, you can actually create really long conditionals as long as you follow the rules. Oh, lights went out again. There we go. Okay, so how do I make assumptions in a derivation system without messing it up? All right, well, when your cursor is blinking and it's your turn to make a move, you can make an assumption and start a subproof on any line, and introduce any more assumptions within that subproof. So you can make as many as you like. I say except the last one. What that means is that you cannot finish your derivation without discharging every open assumption. Before you're done and you declare victory, you have to make sure all your proofs are closed by moving back towards the left, towards the main line. How do you do that? Well, if you're building a conditional, that means you take your assumption and you go if assumption then, and then you choose one of the things you've derived. All right, so all subproofs must be closed by the time the proof is over, and you can't finish with an open derivation, with an open subproof line. And you can close them really at any time, providing you follow the rules, right? And once closed, by closing them, you can create the conjunction. Not the conjunction, you can create the conditional. But there's also other rules that will require assumptions. We haven't looked at them yet. But they are roughly biconditional introduction, and then two negation rules, negation, elimination, and negation introduction. We're going to get to those. But subproofs are going to be really one of the most powerful tools we have in our derivation system to demonstrate various properties of arguments, most prominently validity. So also, if you're nesting subproofs and you have a whole bunch of subproofs, I'm going to give you examples, don't worry. You must close them in the order that you of most recently opened, right? So as you're moving to the right and you're creating more nested sub-assumptions, you're going to have to close the most recently opened one to get back to the main line, right? And once you close the subproof, you can't make reference back to them. Okay, let's see how this actually works in practice. Okay, so there's a big highlighted mistake here. So line 6 here makes a mistake. This is the same argument we were looking at, right? If P then Q, if Q then R. I've assumed P, I get Q and R. Can I discharge Q and R? No, you can't use conditional introduction to discharge the assumption P, right? This makes line 6 assert that Q and R are definitely true. But the premises don't actually show that Q and R are definitely true by themselves. What we've said is Q and R would be true if P would be true, which is different. However, you could assert if P then both Q and R if you used on lines, right? So if you extended the subproof and I did conjunction introduction on lines 4 and 5, then I would get Q and R, then if P, then Q and R. That is entailed by the premises, but not Q and R itself. So that, right, line 6 here is a mistake. All right. So here's another fairly complicated proof. Again, I don't have an interpretation for this sentence. We're just playing with the symbols at this point. But I know that for a fact that the what's on line 7, the conclusion there is a logically valid derivation of my premise. So my premise is if both G and H are true, then K. And what I want to derive is if G is true, then if H is true, then K is true. What does any of this mean? I don't know. Again, I really want to emphasize that it's not important that you have an intuitive understanding of the if-then sentence. So you have like, okay, well, let's give it an example. Like, if George is tall, then if Harold is hungry, then forget about all that. Look at the main logical operator. Look at the logical form of the sentence, right? The trick is you're going to approach this too intelligently, and you have to actually pretend that it's a game with rules, and that you can only use these rules to achieve your objective. So, what is my target sentence? It's a conditional. I want to derive a conditional. What is the antecedent of that conditional? It is G. So I know that the first move I'm going to have to make when the cursor is blinking for me at line 2, I'm going to want to say, okay, the next sentence, the sentence I want starts with a G if. So I'm going to want to assume G and see if I can get H and K. However, at this point, it might be a little tricky because you have that, but what do you do next? Well, here's a nested subproof, right? right? So you can introduce another one. Okay, so the next thing I want to build, you have to be strategic here. Okay, so I want to build if G, then if H, then K. So it's a conditional inside a conditional, right? It's a dream inside a dream. This is what's that movie where they get into the Chris Nolan movie, Inception? There's some Inception stuff right here. So I'm going to want to assume H, right? There's a second vertical line here, right? So it's an assumption within an assumption, within a soft flour tortilla. But now that I have G and I've assumed H, I can actually draw on what I've assumed previously to the left-hand side and use conjunction introduction to create this AND sentence, G and H. But if I have G and H, I have K by conditional elimination, right? So where did the conditional elimination come from? I have G and H. I got H because I assumed it, I got G because I assumed it. All this is totally legit because it's still happening on the assumption lines. If I have G and H, I have K. So if H, then K, right? Because now I'm discharging the assumption. Hey man, it turns out if I assume H, I get K. So now I have if H, then K. So if I assume G, you know what I can do? I can get if H, then K. So if G, then if H, then K. This is a really unintuitive proof. It's complex. It requires a subproof within a subproof. But if you want to derive a conditional within a conditional, all you need to do is just have two assumptions, introduce them, and then break them back down again. All right? So just again, have a look, pause the video, and just kind of narrate to yourself the steps here. Right? Look at your target sentence, understand its structure, that it has the main logical operator a conditional, and the secondary logical operator is another conditional. Then you'll see why we assume, and then we start discharging. Okay. So we have conditional introduction. It requires we assume something hypothetically, and then anything we can construct on the basis of that hypothetical can then be put back on the main line or the previous line, if it's a nested proof, as a conditional. If P, then Q. Therefore, if P, then Q, right? We're just reiterating what we discovered. Okay, negation, elimination, introduction is very similar. It requires a conditional proof strategy. So what we do, and this is going to be interesting, it's very similar to the shortened truth table method, is we're going to assume the opposite and derive a conclusion. The basic strategy here is that we assume something, anything you like. And that's a really powerful tool because you could literally assume anything. It doesn't have to be an atomic sentence. You can assume a whole sentence. You can assume anything as complex as you like. And if you can derive a contradiction from that, then what you can do is discharge, go back to the previous line or the main line, the opposite. By which I mean a negated or an unnegated version. So suppose I introduce something P. Then using that I get Q and not Q. And that could be anything, as long as it's a contradiction. Right? It could be P and not P. It could be the same thing over again. So if I have an assumption that leads to a contradiction, the other one must be right. So if I assume P and I get a contradiction, then not P must be the case. Why is that? Well, think about it this way. There's only two truth values. If an assumption leads to a contradiction, then the opposite of that assumption must be the case. If I assume not P and I get a contradiction, I get to discharge P. This will all be more clear with an example. So here's an example of how this might work. Now, the first thing you should always do is look at the target sentence, what I want to derive. The target sentence, I've been using that, but that just kind of means that it's entailed by the premises, or another way of saying it would be that it's the conclusion of an argument. If I want to derive N, what I want to show is that N is a conclusion of an argument with these premises here, or that if I can show that deriving N means that it's a valid argument, assuming N is the conclusion of an argument with these premises. Okay, so what I want is N. Now I look at the premises, and I see a whole bunch of conditional statements. Whew, I take a deep breath because that's annoying. Conditional statements are annoying to deal with. If I had a bunch of AND statements, I could be like, well, all right, I'll just start breaking things down and we'll see what happens. If I had, a disjunction, and then I could maybe use disjunction elimination, that'd be useful, but I don't have any of that. So how am I going to find N when I have a bunch of conditionals? So once you start eliminating other strategies, you might tell yourself, you know what, I'm just going to assume the opposite and hope for the best. right? Because unlike a truth table, the derivation system leaves it up to you how you're going to proceed. You have to make a decision about what move and what rule you're going to deploy. It's more open-ended that way. So the cursor's blinking, you're player one, and your goal is to derive N for 500 XP and flaming meteor sword, fellow kids. So you want N. How do I get N? Well, in a case like this, and I have the premises and I'm telling you to derive N, I'm telling you implicitly that it's a valid argument, so you know it's possible. You know, right? You know for a fact that N can be derived from the premises. So that's an important kind of piece of information here. I'm saying this argument is valid. Show it. So we have a bunch of conditionals. So what am I going to do? Well, I'm going to assume the opposite. And I'm going to use negation elimination. If I assume the opposite of my conclusion and show that a contradiction follows, then the conclusion, right, I should be able to get N if I assume the opposite. So let's assume not N. What happens? Well, if I assume not N, I have actually a bunch of things start happening. I have not N, and if not N, then S, so I get S. If I get S, then I have C, right, through, again, conditional elimination. If I have C, then I have N. Whoop, now I have my contradiction. If I assume not N, I actually can prove N. That's weird. Now, your contradiction could be anything. Your contradiction doesn't need to be a separate thing from your assumption. Anything could be the contradiction, as long as it's a sentence and its exact negation. It doesn't have to be an atomic sentence either. It could be a complex sentence and its negation. So, for example, imagine on line 3 I had if C, then either N or Z. Then I could use conditional disjunction introduction, maybe. Maybe I'd have to work out that proof. I just ripped that. So I want N. Let's assume the opposite. Assuming not N gives me S from the conditional. It gives me C from the conditional. It gives me N, but I've assumed not N. Whoops, contradiction. Let's just make it explicit. So assuming not N led me to a contradiction, so the opposite must be true, right? And again, you can use a partial truth table to confirm this if you're not sure. So that's an example of how negation elimination would work. Assume the opposite, derive a contradiction, right? And then you can discharge the thing you were after. All right. Now, that was negation elimination, but of course negation introduction works the exact same way, right? I assumed in this case not N, but I could have, right, if the proof had been different, I could have assumed N and then discharged not N. Okay. So, biconditional introduction is a more complicated one here because it requires two subproofs, but the idea is very straightforward. The idea is that if P implies Q and Q implies P, then P if and only if Q. Now, if you have these two conditionals already, that's awesome, but you may or may not have them. So let's show that P if and only if Q on the basis of these two disjunctions. So I have either not P or Q, and either not Q or P. Now, you might remember that these are basically hidden logical equivalencies, right? Either not P or Q is just if P then Q, and either not Q or P just is if Q then P. So I'm just trying to be clever here. But how do I prove it? I can go P assumption, right? And if I have P, I can run disjunction elimination here, because P, but it's actually not P. And I don't insist on double negation, right? I wrote that's a legit move, but it's pretty obvious that either not P or Q, but P, so Q must be the case here. This is just a case of disjunction elimination. So if P, then Q. Now I don't discharge right away. I don't discharge if P, then Q. Instead I wait and I do my other thing. I do it again. I say, well, let's assume Q. If Q is true, then P is true. Therefore, if P, then Q. So how biconditional introduction works is actually pretty simple. I have to do like two conditional introductions. Right? So if I can derive one from the other and vice versa, I can just go ahead and introduce the conditional. So if I want to, the biconditional. So if I want to introduce any biconditional, if P if and only if Q, I have to assume P derive Q, assume Q derive P, then and only then can I discharge P if and only if Q. Okay, so here are all your favorite rules in one place. So you can refer back to this slide, timestamp 30 minutes. and slide 28. So what we have is, right, disjunction elimination, disjunction introduction. Did I just say disjunction? Conjunction elimination, conjunction introduction, right? So if I have an and, I can give you one side or the other. I can combine two statements into an and if I know they're true. I can, if I know that one side or the other of a disjunction is false, right, I can give you the other side. I can always introduce a disjunction. I can dismantle a conditional if I have the antecedent. And these are all the non-conditional proofs on top here. And if I have a biconditional, I can eliminate it. If I have one of these, then I can give you the other. And all the conditional proofs are here. So negation, introduction, right? I assume P, I get a contradiction, I get not P, so I'm introducing a negation. I can eliminate a negation if I assume not P, get a contradiction, just get P, so I'm taking this negation and removing it. So, right, this is just proof by contradiction, very powerful tool. If I assume P, I can get Q, I can discharge P then Q. And if I prove P, if I can get Q from P and P from Q, I can get P if and only if Q. All right, that was super fun to listen to, I'm sure. And on the, is it 30 minutes? Okay, we're going to stop here for the next video. Thanks for watching.